Let us now proceed to discuss relative motion in two dimensions. So to derive the necessary formulas, let's consider this coordinate plane, in where point O is the origin and also the reference point in describing the position of any particle. If we have particle A, we can denote its position as S sub A. Take note that this arrow vector for the position vector is drawn in where its tail is connected to the reference point and the arrowhead is pointing to the particle. If we have another particle B, then its position vector can be designated by S sub B. In the same way, this arrow vector is drawn such that its tail is connected to the reference point and its arrowhead is pointing to the particle B. So both S sub A and S sub B represents the position of the particle, and we can also call these vectors as absolute position vectors. If we are going to draw the position vector of particle B with respect to particle A instead of the reference point, then we can draw its arrow vector by connecting the tail to the new reference point, which is the particle A, and the arrowhead pointing to the observed particle, and we can designate that as S sub B over A. So take note in the subscript that the B here is in the numerator, which means that the observed body is the particle B, and particle A is in the denominator, which means that the observer is the particle A, or the observer is on point A. So for this example, XOY, or the coordinate plane, is a absolute reference, which means that this plane is not moving or is at static, while particle A and particle B can change its position with respect to time. Then the vectors pertaining to absolute motion, which is S sub A and S sub B, they must be connected tail to tail. So later in our problems, if we are going to include in our solution the absolute vectors for velocity and acceleration, we must take note that we have to connect the arrow vectors of all vectors that is pertaining to absolute motion. We must connect them tail to tail before we proceed with the computation. Now, if we are going to derive the formula for the relative position of particle B with respect to particle A in terms of absolute positions, then we must apply vector addition, in where the sum of S sub A and S sub B over A will just be equal to S sub B. If you can recall in physics, the sum of the vectors that are connected head to tail will be equal to a resultant vector, in where that vector has its tail connected to the tail of the first vector and the arrowhead connected to the arrowhead of the last vector. So for this example, S sub B represents as the resultant of the sum of S sub A and S sub B over A. So by rearranging the terms, we can now have the formula for the relative position, which is equal to S sub B minus S sub A. So take note that the same with the relative motion in one dimension, the pattern of the subscript still applies in this case. So in the right side, the first term is the position of the particle designated as numerator in the subscript, then minus the position of the particle that is designated as denominator in the subscript. If we now differentiate our equation in terms of time, then we will be able to get the formula for relative velocity. So even in this formula, the pattern of the subscript still applies. Again, if we differentiate our formula with respect to time, then we will get the formula for the relative acceleration. As you can observe, these three formulas are very similar to the formulas that we use for the relative motion in one dimension. However, for this case, we must consider that each vector here will have its horizontal and vertical components. Therefore, in our solution, we must also consider those components before we arrive at the final answer. In dealing with the computations of relative motion in two dimension, Let's use the formula for the relative position, because the succeeding flow of analysis will be just the same for the formulas of relative velocity and relative acceleration. So the first thing that we will look at is that each vectors in this formula has its own horizontal and vertical components. Therefore, we can write the each vectors in this formula in terms of their components or in IJK format. In this way, we can highlight the horizontal and vertical components of each vectors. So after writing the components of each vectors, we can now go back to our formula and use our formula by component. So that means that we will apply it in terms of x component and y component. Let's say the first thing that we will look at is the horizontal component of each vector. Therefore, the horizontal component of the relative position is equal to the horizontal component of S sub B minus the horizontal component of S sub A. In the same way, the vertical component of the relative position is just equal to the vertical component of S sub B minus the vertical component of S sub A. So if we have written each vectors in the formulas in terms of their components, it will be much easier to make use of the formulas by components. Let's say that for this example, we have a negative value of the x component of the relative position and a positive value for the vertical component. Then we can make this sketch in order to draw the correct direction of the relative position of particle B. By rectangular method, we can now draw the correct direction of S sub B over A. It is possible in your initial sketch that you will make errors in drawing the vectors. So the causes of those errors is that the vectors in your initial sketch might not be drawn into scale, and that the angle of inclinations of each absolute vectors are only approximated. So there is a possibility in your initial sketch for this example that you might consider the arrow vector of its position to be much longer or have a greater magnitude, and that its angle of inclination will be smaller compared to what is drawn. So in that case, if the arrow vector is much longer in your drawing and that the angle of inclination is smaller, then particle beam will lie on the right side of particle A instead on the left side. So the resulting position vector of this particle will be as follows. Now, if we draw the relative position of particle B with respect to A, then this will be the direction of the relative position. So compare now this direction with the previous direction. For this drawing of the relative position, the x component of S sub B over A must be positive, and that the y component of S sub B over A must be also positive. So by using the obtained values of the x and y component based on computation and also taking note of the sign, we will be able to determine the correct direction of the S sub B over A, or the relative position, or even relative velocity and relative acceleration in other cases. After determining the x and y component of the relative position, we can now compute its magnitude by using the Pythagorean theorem. And when it comes to the direction of the relative position, we can solve for the angle of inclination. And for this example, let's say represented by angle theta with respect to the horizontal. And by applying trigonometry, angle theta is just equal to arctangent of the absolute value of the fraction of y component over x component. Let us now apply this flow of analysis in our third sample problem. So we have here two ships leaving point O at the same time. Ship A sailed along 45 degrees north of west with a velocity of 18 kph. Ship B sailed due east with a velocity of 9 kph. Determine the relative velocity of ship B with respect to A in kph. So we are given the velocities of the ship A and ship B, and by looking at their directions, these two velocities are not existing in one dimension. Then we are required to solve for the relative velocity of ship B with respect to A. So in our solution, we will draw the arrow vectors of velocity of ship A and velocity of ship B. So take note that this point O represents the reference point described in the problem. So for ship A, V sub A must be inclined 45 degrees with respect to the horizontal, while the arrow vector for V sub B is directed to the right along horizontal. In preparation for our alternative solution, let's just indicate the angle between V sub A and V sub B. So now let's draw the arrow vector for the relative velocity. So this will be the drawing of the arrow vector for V sub B over A. Take note that the observer is on ship A and the observed body is ship B. Therefore, the tail of this arrow vector must be connected to the arrowhead of V sub A, while its head or arrowhead must be connected to the arrowhead of V sub B. So to begin our computation, we will just look at the pattern of the subscript to write the needed formula. In this formula, we must take note that each vector has its own x and y components. So therefore, we will make use of this formula by component. So let's start with x component. So the x component of the relative velocity is equal to positive 9 minus the x component of v sub a, which is equal to negative 18 cosine 45 degrees based on its orientation here in this drawing. So this is equal to positive 21.73 kph. Next, along vertical, the y component of the relative velocity is equal to 0 minus positive 18 sine 45 degrees. So this is equal to negative 12.73 kph. So based on our result with the components, we can now draw the arrow vectors of the components to determine the correct direction of the relative velocity. Okay, so by drawing these arrow vectors of the components and by rectangular method, we can now draw the correct direction of our relative velocity. Let's denote the angle with respect to the horizontal by angle theta. So for the magnitude, we will just apply the Pythagorean theorem and substitute the values of the components, and this will give us a magnitude of 25.18 kph. While for the angle of inclination, we will just apply trigonometry and take note that we will consider only the absolute values of the components. So this will give us theta equal to 31.36 degrees. With this value of magnitude and angle of inclination, we can now express our final answer equal to this magnitude and with this direction. So another way of solving this problem, aside from using this formula, is by treating this triangle as a geometrical problem. So now to solve for the magnitude of the relative velocity, we will just apply cosine law. So by cosine law, we will be able to write this equation, and by substitution, the only unknown variable will be v sub b over a. So computing for the magnitude of relative velocity, we will get the value of 25.18 kph. Now about the direction of v sub b over a, we will denote its angle of inclination with respect to the horizontal as angle theta. Okay, so if this is angle theta, the interior angle at this vertex must be also equal to angle theta. So using the interior angles, we will apply sine law to solve for the value of theta. So by sine law, we will substitute the obtained value for the relative velocity and also the given value for v sub a. This will leave us with only one unknown variable, which is theta, and that will give us theta equal to 30.36 degrees. So with this magnitude and this angle of inclination, our final answer is just the same to the final answer from the previous solution.